Okay, so now we'll do a second application of the principle that we talked about earlier, the fixed point principle. So the proposition, let me recall the fixed point principle this time. G is a finite group acting on a finite set X, and G is a P group. Then we said the cardinality of X. So here everything is finite. Cardinality of X and the cardinality of the set of fixed points are congruent to each other modulo P. Okay, so this was the principle, and now we had one nice application of this last time, which was a proof of Fermat's little theorem. Now here's a second application of this, again sort of a number theoretic statement. So it says the following: let n and r be some natural numbers. P is a prime, the same prime that we have fixed throughout. Then the binomial coefficient Pn choose Pr is congruent to the binomial coefficient n choose R mod P. Okay, so recall the binomial coefficient n choose R by definition is just the number of ways of choosing R objects from n objects. So that's just n factorial by R factorial n minus R factorial, number of ways of choosing n distinguishable objects from which you have to pick R. Okay, so now the statement here is really something about the fact that these two numbers are always congruent to each other, number of ways of picking PR things from Pn things, and the number of ways of choosing R from n. They turn out, well, they won't be equal of course, but they are congruent to each other when you look at them modulo the prime P. Okay, so let's prove this again as an instance of this fixed point principle. So what am I going to try and do? Well, the same thing we did earlier. We'll try and construct a set X whose cardinality is the left hand side, Pn choose Pr, and we'll construct a group, a P group action on it, such that the set of fixed points gives you the right hand side, n choose R. Okay, so we have to manufacture the following two things. We need to manufacture a group G, and we need to manufacture a set X such that its cardinality is Pn choose Pr. Right? That's the first step, and then we must hope that the fixed point set turns out to be the right hand side. Okay, so let's do this. So for a start, again, like last time, I will just, in the previous example, let's just pick the simplest cyclic group of cardinality P as our P group. So this is just 1 sigma sigma square sigma to the P minus 1. So of course this is a P group, and now I need to construct a set whose cardinality is Pn choose Pr. Okay, so how am I going to choose that set? Well, first let's construct a set of cardinality Pn as follows. So I will think of it in the following manner. So let's construct a rectangular grid of dots. So imagine I have a grid like this, okay, and so some number of rows, some number of columns. So let me assume it's got P rows and n columns. Okay, so I have a rectangular grid of dots. So of course this has Pn dots in all. Okay, so I'm going to take my set Z to be the set of all the dots in this diagram. So first my set Z is the set of all dots in this grid. Okay, that's my set. The elements are the dots. Okay, so we'll try and give some sort of geometrical construction, and then of course, having done that, the set X itself can be chosen to be all subsets of the set Z of cardinality PR. Okay, so that's the next step. So maybe we should just do this by way of example, just to get a better handle on what's going on. So the proof is best illustrated by an example. So let me actually choose concrete numbers here. Let me take n to be 4, let me take R to be 2, and let me take my prime to be 3, so that I can actually draw a nice figure here. So let me draw the first thing which is my set Z. So what does Z look like? Z is all points in a 4 cross 3 grid of dots. So this is my 4 guys in the first, let's see, where are we? Yellow. Okay, so this grid of dots is going to be my set Z. So it's got exactly Pn dots. So observe, this is a 4 columns and 3 rows. So this is a 3 cross 4 grid of dots. Okay, so the dots themselves they form the elements of my set Z. Okay, so I have my set Z here. So let's copy this. Here's my set Z. Okay, now what is it that I want to define as my set X? So X, of course, remember, has to have cardinality Pn choose Pr. Okay, so that's what I know about. So Z has cardinality 12, which is Pn in this case. The set X that I'm interested in constructing should have cardinality Pn choose Pr, right, which is the number of ways of choosing PR objects out of Pn objects. So this is the number of ways of choosing 6 objects out of 12 objects. So 6 dots out of these 12 dots. So I'm going to think of all these 12 dots as being distinguishable objects here. I just colored them with 3 colors to say these are the 3 rows, that's it. Okay, so what should my set X look like? This is just going to be the collection, the set of all A, subset of Z. So subsets of the dots, some collections of dots, so that the cardinality of A is 6. In other words, this is the set of all collections of 6 dots out of these 12 collections or sets. Okay, so set of all such collections, and observe the cardinality is exactly 12 choose 6, because that's the definition of the binomial coefficient. Okay, so what are some examples of elements of A, for example? So A is, in this case, I need 6 dots, right? So let's see, suppose I take the 4 guys in the top, this one green, this. So this is an example of a subset A of cardinality 6. So this subset A would be an element of X. Okay, similarly, maybe I could take these 3 and these 3 together. This is another choice of A, and so on. So you get the idea here. So I can take these 6 dots or any collection of 6 dots among these 12. All such collections put together, that's my set X that I'm going to talk about. Okay, so I have a set of the correct cardinality. We are only trying to match cardinalities so far. Now, the set X, of course, is more complicated than the set Z. So remember, the set Z was, well, what was it? It was just it was just this grid, right? So this is your set Z. Just single dots. X is more complicated. The elements of X are now collections of 6 dots at a time. Okay, so we'll come to X, but what is it that we eventually want to do? We want to define an action of the group, and remember, the group in this case is the cyclic group. So in this case, P was 3 in our example. So let me try and construct an action of the cyclic group of 3 elements on the set X. But before I do that, let's first work with Z as a starting point. So this is what I eventually want to understand how to define an action on X, but for a start, let's define an action on Z. So how do you make the cyclic group of 3 elements act on this set Z of 12 dots? Well, there is one obvious action. What is the obvious thing you can do? Well, what does C3 look like? C3 has 3 elements, remember, 1, sigma and sigma square. Okay, sigma is the generator, sigma cube is the identity. How do you make this group act on Z? Well, it can sort of cyclically permute the rows of this diagram, okay, by cyclically permuting rows. So what do I mean by that? Okay, so let's come back to this next. Let's first figure out how to define an action on Z. So how do we cyclically permute rows? What do I mean by that? If I take my element sigma and it acts on this dot here, this red dot A, well, I'll define it to be the dot that's right below that dot here. So I'm moving a dot in the first row. The action of sigma just takes it to the corresponding dot in the second row. So this guy is my A dash, for example. So similarly, how does sigma act on this dot? Well, it just moves it down to this other guy. Okay. Now, how does sigma act on dots in the second row? What does it do to a green dot? It just moves it to the corresponding dot on the row below. So this dot here under sigma, so if I call this B dash, it will just move to this dot B double dash. Okay, so if I call the dots on the first guy as A, B, C, D, these are all dashes, these are double dashes maybe, then the action of sigma is the following. It moves the first row to the second row elements to the third row, and it moves the third row elements back to the first row. Okay, so sigma A is A dash, sigma acting on A dash is A double dash, etc. So I've sort of just visually defined what sigma does for you. It moves the red dots to the corresponding green dot below it. It moves the green dots to the corresponding yellow dot below it, and it moves each yellow dot to the red dot, which is sort of cyclically below it, meaning if you sort of think of it as being on a circle or a cylinder, then the yellow dot sort of moves to the corresponding red dot that's going to be in the first row. Okay, so this is what I mean by cyclically permuting rows. So this is the action of sigma, and of course sigma square will just have to do this twice. So what will sigma square do? Well, it will sort of do sigma 2 times. In other words, how will it act on a red dot? Well, it will move it to the yellow dot, which is 2 steps below it, etc. Right? So I hope it's visually clear. I've tried to not make it overly formal. So if you of course you want, you can sort of write this all out in very formal language. But for now, let's try and understand the main idea here. If I have a grid of dots like this, then I can make the cyclic group of cardinality 3 act on it by sort of moving so here's my grid of dots. I act sigma does this, it moves each row 1 row below to the row that's below it. Okay, so this is the action of sigma. Okay, now again exercise, check that this is an action. So check this defines an action of the group G, in this case C3, on the set Z, which is this set of 12 dots. Okay, and of course you can see here there's nothing special about 3 and 12 and so on. I could have done this with general N and P and R. I mean, R hasn't entered the picture yet, but I could have done this with any N and any P. The corresponding cyclic group Cn, the grid now has N rows, right? Or rather P rows and N columns. So it has P rows. The cyclic group of cardinality P just moves, the generator sigma moves each row of dots to the corresponding row below it. Okay, so it's again easy to check that this defines an action, that the 2 properties of an action are satisfied. Now let's come to the question we are interested in. How do we define an action of the cyclic group on the set X here? Okay, so I need an action of C3 not on Z itself, but I want to understand how to define an action on X. And what was X? If you remember, this was just a set of all 6 element subsets of Z, right? All collections of 6 dots. So how do I do that? Well, there's again the obvious thing. If I have a set of dots, so here's my set of dots, and let's say I have a collection of 6 dots. So for instance, what shall we do? So suppose I take these 4 and these 2. Here's a collection of 6 dots. So if this is my subset A, the collection of 6 dots, then there is again an action of the cyclic group on this by what's called the element wise action. Okay, so if I have, so this is, maybe it's worth writing out as a general thing, a general fact to observe, that suppose a group acts on a set X, then the group in fact acts on given this, I can make the group act on what's called the power set of X, right, which is the set of all subsets of X. And how do I make it act? As follows, by if I take a group element G and if I take a subset A of the set X, then the definition of the action is it just acts element by element. Take each element of A. So this action is defined for every subset of X. In other words, for every element of the power set. Okay, so this action here, again check it's an action. This is called the action on subsets. Okay, so this is the action on subsets of X, and this action is just the element wise action. It just acts on every single element of the subset, and each element will now be transformed to some other element, and you take the new collections of elements. So let's do this by example. If A is this collection of 6 dots that I have just marked here, then what is sigma acting on A, for example? Okay, so by definition, what does sigma do to these 6 dots? Well, sigma will take, let's draw this separately. So what will sigma do to each of these dots? Sigma will take this red dot to this green dot that's right below it, right? So this element goes here, this element goes here, this goes here. Well, in fact, this goes here, and this green guy goes to the thing below it. This yellow fellow in A goes to the one above it. Okay, so if I act sigma on each of these elements, what are the new elements I get? Well, I get these 3 green dots, I get this green dot, I get this yellow dot, and the yellow dot goes to the red dot above, so I also get this red dot. So this new set here, which has, let's try and clean this up a little bit. So the action of sigma on A is just obtained by acting sigma on every element of A and seeing what are the new dots that you get. So that's the set sigma A. It's those 4 green dots, 1, 2, 3, 4. There's a red dot on top, there's a yellow dot on the bottom. So this collection of 6 dots is exactly sigma of A, where A was the original subset. A was this thing, the thing I had marked originally in blue. Okay, so I hope the definition is clear. You just act element by element, you act that group element on each element of the subset. Okay, so this is called the action on subsets. And so what have we done here? To recall, we said we have an action of C3 on the set Z of all dots in the grid, and from here we have an action on the subsets. Well, there is an action on all subsets, but in fact you can also restrict this to get an action on subsets of a given cardinality. Okay, so I mean, as is clear, if I have a collection of if I have a subset of Z which has 6 elements and I act a group element on that subset, the new subset also has 6 elements. Okay, so this is the action on subsets of a given cardinality. So anyway, this is something that you should check in this case, that because I have an action of C3 on Z, I also have an action of C3 on X, which is the collection of 6 element subsets of Z. So we are close now. We already have a P group and we have an action of that P group on the set X, whose cardinality is exactly Pn choose Pr. This cardinality is Pn choose Pr. Okay, now the question is, I mean, now we are ready to apply our fixed point principle. So by our proposition, or the fixed point principle, let me call it that, I know that the cardinality of X is congruent to the cardinality of the set of fixed points modulo P. Okay, now let's again do it in this example. So what is our set X? X is, well, the collection of all 6 element subsets. So its cardinality is, as we know, 12 choose 6. Now what are the fixed points? So that's the question. So let's try and understand what the fixed points of this look like. So here's a grid again. Okay, so here's the question. Suppose I have a 6 element subset of these 12 dots. So let's take A to be a subset of this grid of dots, and A, let's say, has 6 elements. Okay. Now the question is, when does A belong to the set of fixed points? What does it mean to say that A is a fixed point? Okay, so let's try and figure that out. If A is a fixed point, in particular A is fixed, this means that A is actually fixed by sigma, the generator of the group. Okay, in fact this is enough. If it's fixed by sigma, then it's also fixed by sigma squared, sigma cubed, and so on. So, but let's just look at this condition. A is fixed by the element sigma of the group. Now what does this mean? So if you recall what the action of sigma was, it moved dots in a given row to the corresponding dots in the row below it. Okay, so how can I choose 6 dots? So this is my question. How can I choose 6 dots from this diagram so that when I move that configuration of 6 dots 1 unit down, sort of cyclically, the new configuration of 6 dots coincides with the original configuration of 6 dots. Okay, so the question is how to choose a configuration. Well, sigma A is A just means that A is a configuration. So let me write it that way. This means A is a collection of 6 dots which remains invariant under the action of sigma, right? So which is under cyclic permutation or cyclic rotation, whatever the word is. Okay, so let's just try and look for examples. What does that mean, right? A must contain some 6 dots. So let's see. Suppose A contains this red dot. Suppose this dot is an A. Okay. Now what can I say about the other 5 dots? Well, observe firstly that A must be invariant under this cyclic rotation. Means as soon as I have this red dot here, this green dot and this yellow dot must both be in A. Okay. Why is that? Because if either of them is missing, then when I perform sigma on A, you will see that the new configuration is not the same as the old configuration. Okay. For example, if A has this red dot here and suppose it doesn't have this green dot. Okay. So imagine this red dot is in A, but this green dot is not. Okay. Then what will happen if I perform sigma on A, then the new set sigma A will contain the green dot, okay, but the original set A does not contain the green dot. Okay, so this property here that this A must be a collection of dots which is invariant under cyclic rotation means the following: as soon as A contains any dot, say the red dot, then it must contain the other dots in that column. So this automatically means this is there, this automatically means this is there. Okay, so all 3 guys in a column are automatically there. Okay, so we have figured out 3 elements. Now A has 6 elements. Let's assume some other element belongs to A. Let's say this dot was in A. Okay, by the same reasoning, if I apply sigma to A, to that yellow dot, when I apply sigma, it will become the red dot. Okay, which means since the yellow dot is in A and A is invariant here under the cyclic rotation, it means that this red dot must also be in A, and by the same token the green dot must also be in A. Okay, so as soon as any dot in any column is in A, every other dot in that column is also automatically in A. Okay, in other words, we conclude that A must be a union of columns in Z. You take this grid of dots and you take some columns, take the unions of the full columns. You cannot have partial columns. Okay, so think about this final conclusion a little bit and convince yourself by looking at a few examples that this is indeed the case. So the only way in which A can be a fixed point is if it is a union of columns. Okay, and observe the reverse inclusion is obvious, that if it is a union of columns, then of course it's invariant under the action of sigma. Okay, now what does that mean? A had 6 elements, remember, and if it has 6 elements, then since the cardinality of A is 6 and it's a union of columns, A must be a union of how many columns? Well, each column has size 3, so it must be a union of 2 columns. Okay, so observe this is exactly the number r that we are talking about. 6 is the number PR. Okay, if you did this in general, each column has p dots and A was a subset of cardinality PR. That means A must be a union of R columns in general. Okay, in our example, it is a union of 2 columns. So therefore, what have we concluded? What are the possible elements? What are the elements of the fixed point set? Well, it's all those subsets of Z such that A is a union of some 2 columns of the grid. Okay, like I said, in general, it's R columns of the grid. Well, what does that mean? How many ways, how many different A's can you choose? So in general, the grid has, here for example, the grid has 4 columns. So what are all the various possibilities for A? It can be a union of the first 2 columns, for example, or it can be the union of this and this, or the union of, say, this column and the third column, and so on and so forth, right? So the number of different ways of choosing 2 columns out of the 4 columns. So this is, as you can see, it's just take the 4 columns that we have and choose any 2 out of them. So that's going to be the total number of ways of manufacturing elements A which satisfy this required condition. Okay, and again I have demonstrated all this by example, but in general, if I did this in general with N and P, what we are going to do is you have N columns in Z and you have to choose R columns out of them. Okay, so just repeat the argument for the general case. Okay, so all this is sort of, I mean, I'm trying not to do this overly formally and so on, just try to give you a visual geometrical idea of what's going on. But finally, I hope you will convince yourself that we have in fact proved the following, that so what have we done in the end? We have constructed a set X which is acted upon by a P group, which in fact is just a cyclic group here. X has cardinality, so this set has cardinality Pn choose PR, which is all configurations of PR points, and the cardinality of the fixed point set is exactly N choose R. Okay, so we have managed to manufacture this, and so finally by the fixed point principle, what this means is that Pn choose PR, that's the cardinality of X, is congruent to the cardinality of the fixed point set, which is N choose R. Okay, so that's sort of the second example, and this will sort of come back when we start talking about Syllo's theorem and so on. But until then, just think of this as a nice number theoretic consequence of the fixed point principle.